Today we're going to get an introduction into organic chemistry. Organic chemistry is the chemistry of carbon compounds. Now, we used to classify compounds as being either inorganic, which means they were composed of minerals, or organic, meaning they came from a living organism. And early chemists thought there had to be some kind of vital force that could only come from living organisms that was required in order to make or synthesize an organic compound. But in 1828, it was just proven when Friedrich Wöhler, a chemist from Germany, synthesized urea by heating an inorganic compound, ammonium cyanate. So that was our first indication that organic compounds did not have to come from living organisms. Now, today there are more than 16 million organic compounds as opposed to about 600,000 inorganic ones because of carbon's variety and complexity of bonding with other elements. So, over 90% of the compounds on Earth are organic compounds. So, it becomes a very important area of chemistry. Now, in AP, we don't need to know a whole lot about organic, but the things we do need to know are important. So, let's look at some things. First of all, we've got methane and ethane here, which are going to show us the covalent tetrahedral structure of these types of organic compounds. And carbon is always going to be the center. Methane ends up looking like this with these covalent molecules in between. Carbon is one of the few elements that can bond to itself, other atoms like it, other carbon atoms. So we have two carbons bonded together, and then the hydrogens will end up always occupying the outside of those molecules. So there's an example of another carbon compound. Again, it is a tetrahedral structure. So even though we've got it shown here two-dimensionally as being more like a square, it's not. Remember our molecules, our 109.5 degree bond angles for these molecules, and that's what we're looking at. Now we can represent molecules a couple of different ways. We can represent them in what's called an expanded structure, or we can represent them in what's called a condensed structural formula. So for propane, C3H8, that does not tell any story at all about what this molecule looks like. So for an organic chemist, it would be more important to realize that this structure looks more like this. We've got the three carbons will always join up, whatever number of carbons there are, they always attach to each other. And then we're going to line up the hydrogens so that every carbon ends up with 4 bonds. So this middle carbon can only hold 2 hydrogens because it now has all 4 of the bonds that it can have, 8 electrons or 4 pairs. And then the other carbons will be able to hold 3 hydrogens each, which will result in each of these having 4 pairs of electrons bonded as well. Butane will do the same thing. We've got butane with 4. I'll draw it a little lower so it fits. The hydrogens around these end carbons can always hold 3 hydrogens if there's all single bonds involved, while the ones in the middle can only hold 2 each because they are already bonded to other carbons. So that's the expanded structure for these. When we write the condensed structure, we just write 1 carbon at a time with the number of hydrogens it has with it after it. For instance, this would be written as I almost wrote a 3 after it. It's CH3. The next we have another C, it has 2 hydrogens, another C, again with 3 hydrogens. So that would be the condensed structural formula. For butane, it would be CH3 with 2 CH2 groups in the middle and a CH3 on the end. So there's the condensed structural formula for butane. And we'll learn more about nomenclature and how to name these in the next set of notes. But for now, we're just learning to recognize these compounds. And how do we recognize them? We recognize them using something called a functional group. Functional groups are the parts of the particular molecule that are distinctive, that let you know what type of organic compound you're dealing with. And there are several different types. As you'll look here, I have listed a total of 12 different types of organic compounds. Alkanes are made up of all single bonds and in a carbon chain, all single bonds. The only other thing that might be present in an alkane would be a hydride. So it's possible that you might have, besides a hydrogen, there might be a fluorine, a chlorine, a bromine, or an iodine attached. That's really the only other options you've got for an alkane. All single bonds. Carbons and hydrogens, perhaps a fluorine, chlorine, bromine, or iodine thrown in for good measure. Alkenes are quick to recognize. They have a double bond. Somewhere in that structure there are two carbons double bonded. Alkynes have a triple bond. Somewhere in the structure there's going to be a triple bond between two carbons. Alcohols, I know an OH group in inorganic compounds indicates that you're dealing, when it's bonded with a metal, indicates that you're dealing with a base. But these OH groups in organic compounds are going to be bonded to other carbon and hydrogen groups. And when you see an OH anywhere in that structure, you know you're dealing with an alcohol. An ether has a lone oxygen just stuck in between two carbon groups. Sometimes if we don't know what kind of carbon group it is, we'll represent it with an R. For instance, ROR means there's an O stuck in the middle of two carbon groups. So an amide will be very distinctive. You'll see this exact part right here with a C double bond O and an N right there together. Now, keep in mind that N could be on the left. We've always got to remember that we could be viewing this from the front of the board, or we can be viewing it from the back of the board. It doesn't matter what direction we are going, as long as we've got a C double bond O on one part and a C bonded to an N on that same carbon. So that's an amide. A thiol has an S in it. Thiols have an S. Aldehydes on the end of the compound always have this structure, C double bond O with an H attached. That's always going to be at the end. A ketone right in the middle of two other carbon groups. So if we're representing carbon groups with R's, we could say that C double bond O is right in the middle of two groups that have carbons and hydrogens in them. Carboxylic acid, we've seen these over and over. If you're writing them as a condensed structure, that's where we get our compounds like acetic acid, our CHQ. Well, that Cu tells us that we're dealing with a carboxylate, often called an organic acid. And that C double bond O with an OH is the Cu part of those acids, and that's going to be your functional group, the specific group that you're going to find that will allow you to recognize that as a carboxylic acid. An ester looks kind of like an ether and a ketone combined. You've got a C double bond on one side, and along with that C is another oxygen bonded to it. So a double bonded O and a singly bonded O to the same carbon tells you you're dealing with an ester. And amines are derivatives of ammonia, and amines simply have an N in there somewhere. There may be an R group next to it. There may be three R groups around it. There may be an R group and two H's, two R groups and an H, whatever, but that N right there is your indication that it's an amine. Now be careful, remember, notice the difference between these two. And in amidst a bunch of R groups, carbon groups, or hydrogens is an amine. But if it's bonded to a C that's also bonded to an O, double bonded to an O, you're dealing with an amide. Okay, in addition, there's a class of compounds called aromatic compounds. They were initially given that name because many of them smelled good. They had a pleasant odor. What they have is something called a benzene ring. Benzene is C6H6, as it says here. It is a hexagonal ring of carbons. Every other carbon is double bonded. So it's double single, double single, double single with a hydrogen attached. Most of the time we'll see it either written like this, or often, as it's shown below, we'll see it written like this. Now there are lots of different aromatic compounds that have benzene rings in them. They can have lots of other functional groups. If we were studying a course in organic, we learn all about these different kinds of aromatic compounds. We just want to be able to recognize them. So if you see that ring, either in this form or this form or this form, somewhere in it, you know you're dealing with an aromatic compound that has a benzene ring in it. Benzene ring. So how do we recognize these? Let's look at our different types of compounds and see if we can find a functional group that matches. In this first compound, we've got all carbons, but just peeking out in there just one time is a little OH. If you look back at your previous information, you'll see that something with an OH in there as a functional group is an alcohol. So that's exactly what we'd name this, as an alcohol. In the next one, carbons and hydrogens everywhere, but in there is a C double bond O OH group. That C double bond O OH, remember, is our COO. That's the one functional group besides alcohol that we should be familiar with because we've seen it many times. That's our carboxylic or organic acid. It's going to have that, again, C double bond O OH group. So this is a carboxylic, also known as organic. We really need to know it as both names because nobody seems to be able to make up their mind exactly which one they're going to call it. Carboxylic acid. In the next one, we've got all kinds of carbons and hydrogens. The weird group in it is this right here. It's a C double bond O with an O attached to the carbon, but it's not an OH. If it were an OH on the end, we'd be back to this carboxylic acid. But it's not. It's just a C double bond O with another singly bonded O attached to some carbon groups. What does that look like? If we look down here, we'll see that that C double bond O attached to a C that's also singly bonded to an O is our ester. So that is an ester. Many times on the AP test, it will simply show us a structure and just ask us what type of compound it is. And we just have to pick from a list. They might show us this compound and say, is it an alcohol, an ester, an ether, or a carboxylic acid? And we would have to recognize based on the functional group that it's an ester. The next one, lots and lots of carbon-hydrogen groups. The weird part of it that sticks out is this part right here. The C double bond O with the C also bonded singly to a nitrogen. So which one does that one match? If you look back here, you'll see that that one matches our amide. Some people call it amide. So that's an amide or amide. Now the next couple of structures are a little weird. I really don't think you're going to see them on the AP test. But these line drawings, just realize that at every end point and every point, there's a carbon. So there's a carbon here, carbon here, carbon here. If you look at the next one, carbon, 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 carbon. There's just a carbon at every end point of a line and at every bend in the line, there's a carbon. So if you'll look at this then, the only really weird part about it is this part right here that's just a C double bond O. It's not attached, the C is not attached to another N, it's not attached to another O, it's not attached to an OH or an H, it's carbon to carbon. So what is our one that has a C double bond O just stuck out in the middle somewhere with carbons all around it? That's our ketone, just a C double bond O. So going back to this, that's going to be a ketone. This next one has an O stuck in the middle, just a lone O stuck in the middle of two carbons. Look back and see which one you think that would be, with that lone oxygen just stuck out in the middle. And you can see that that's going to end up being our ether, just an oxygen in the middle of carbons. So this is an ether. And finally, on the last one, you'll see it that it's all carbons and hydrogens. And the only thing, it's all single bonds. The only thing that's a little bit different in here is that we've got a bromine attached instead of a hydrogen to one of the positions. If you look back, you'll see that that is a perfect example of an alkane. It's all single bonds and carbons with just the possibility of maybe of a fluorine, a chlorine, a bromine, or an iodine in there somewhere. So this is going to be our alkane. And that's your introduction into organic compounds.